Hi everyone, and welcome to another Understanding Deep Learning seminar. Today, Jaehoon Lee will present to us his paper on explaining neural scaling laws. Jaehoon is a senior research scientist at Google Brain. His main research focus is on fundamental understanding of deep neural networks, actively working on the infinite width limit of neural networks and their correspondence to the kernel methods. In 2017, he joined Google and started a research career in machine learning as part of the Google Brain residency program. Before that, he was a postdoctoral fellow at the University of British Columbia from 2015 to 2017, working on theoretical high-energy physics. Jaehoon obtained his PhD in the Physics Center for Theoretical Physics, Massachusetts Institute of Technology in 2015. Jaehoon, please take it away.
Hi, thank you for the kind invitation to present our work. So previously, I've been mostly given talks on the infinite width limit of neural networks, but since there has been excellent previous speakers on the topic, I'll be presenting on somewhat related but a different topic. So for today, I wanted to talk about our recent attempt to understand and somewhat explain how neural networks performance improve as you scale them up. And I believe understanding the scaling behavior is a fundamental direction for guiding future progress in the field. And so far, theoretical and empirical characterization of neural network scaling laws is quite new and active research area. So my hope for today's talk is that it excites your research interests around these topics. And as I prepared this talk, I realized that the content itself is not that long. So if you have any deeming questions, feel free to ask in the middle, and I'll try to answer them as I go along. The talk will be mostly based on this paper, but also be borrowing results from many related works. Please refer to this archive link in case you want to further dive into the details. Let's start talking about where we are as a field in terms of making progress. For the last 5 to 10 years, we have seen remarkable advances in so-called artificial intelligence-based technologies, starting from breakthroughs in computer vision. There has been a series of major progress in fields such as translation, language modeling, speech recognition, game playing, healthcare, all the way to the complex scientific discoveries. One core recurring theme among this progress has been the use of multi-layer artificial neural networks, commonly dubbed as deep learning. It's natural to wonder what drives this remarkable progress. I'll briefly highlight some main factors. First is data. Neural networks efficiently utilizes large amounts of data. And not surprisingly, with more data, the models perform better. One of the reasons deep learning was able to make remarkable success was ability of large datasets to be trained on. Another factor is the utilization of larger models. Recent history in deep learning has repeatedly shown that as we increase the capacity of the models, the performance improves. There is a general mantra of the bigger, the better when obtaining the state-of-the-art models. On the left plot here shows the performance of one of the best performing family of image classification models called EfficientNet V2. And the plot shows within the same model family, more parameter leads to better performance. And on the right, we have GPT models with varying model sizes evaluated on various benchmark tasks. Here you see the general trend of improvement in performance as the model becomes larger. Closely related is the availability of compute. Here, in the figure from the OpenAI blog, it shows how much compute increased as the function of time in recent years. Starting with AlexNet in 2012, through neural machine translations and AlphaZero, the overall trend shows that it's about 3.4 months of doubling time for a compute increase. You can compare this to Moore's law, which had about 2 years of doubling period. And you can see that compute increase is much faster. So undeniably, the amount of compute used or available is vastly growing. And we hope to best use this compute to make meaningful progress in the future. There's also has been numerous developments in architecture choices, a training algorithm, and other many techniques. Some highlights, for example, are scheme connections, use of self-attentions, adaptive optimizers to learn data augmentations, etc. One could imagine among these numerous choices and techniques, what are the relevant techniques that would still remain relevant in the future? So given current status, why would be interested in studying scaling? As we've seen, more data and larger model often leads to better performance. And also, it seems like larger compute will be the driver for progress in AI systems in the future. Given the situation, we hope to understand various choices and techniques that could scale well when given more compute. This point is well stressed in the essay from Rich Sutton, saying that the only thing that matters in the long run is the leveraging of the computations. So one goal of our paper is to come up with simple theory or description of scaling behaviors in neural networks. We'd like to have some theory or framework to predict future performance given more data or larger models. Our hope is that we want to understand and determine what choices matter that lead to improved scaling, echoing the voice of Rich Sutton. Here's a prototypical example of scaling plot of performance versus model size. Here, there are a few things to notice. This is on the log-log plot and showing a power law behavior. The straight line, the scaling behavior, holds for more than 4 to 5 orders of magnitude. This type of plot can tell how one method can be better than the other when you scale up computations. For example, here we can see that compared to LSTMs, the transformers are better because they are shifted below. The slope is remarkably similar to each other, with some hints that LSTM scaling tapering off for a large number of parameters. So in this viewpoint, for any methods and techniques, we could frame whether they would lead to shifting of these lines or leading to better slope. For the case of better slope, if one can scale the models using larger slope, one could even start with the worst performing models for smaller model sizes, but eventually have potential to outperform the transformer models when scaling once the scaling remains to hold. Today, I found this joke tweet from Borg and LeCun, and it says, if they had convolutions, they had used convolutions, perhaps this language model might only have required 1.7 thousand parameters. Joke aside, one could frame this convolutional architecture actually would lead to more preferable scaling compared to transformer if you made something similar to this. So I hope by now you're convinced that studying the scaling behavior of neural networks is important and somewhat interesting. And the main goal in this line of work is that we like to describe how performance improves with scale. So let's discuss what precisely we mean by scaling laws and how they appear in deep learning. Recall that most physical laws are often seen as scaling laws. Something simple as just computing areas or volumes, or Newton's law of gravity can be thought of as scaling laws. And naively, scaling law just means that having a functional relationship between two physical quantities that scale with each other over a significant interval. However, in more technical terms, scaling law often means that the functional relationship is in the form of power law. Something like y equals constants times x to the alpha displayed in the slides. The scaling exponent alpha is one of the most important number characterizing this relationship. As a warning, I'll be often denoting exponent, pulling out the negative sign, since we'll be interested in how loss decreases as one adds more data or parameters. As we've seen in the comparison of LSTM and transformer plot earlier, in order to see the power law behavior, we can check the functional relationship between two variables follow a straight line in a log-log plot. And in these plots, the slope is given by the exponent alpha. And one notable property of this power law scaling behavior is that this relationship is actually a scale invariant relationship. And in deep learning, recently we are starting to observe more and more of this power law scaling behavior emerge. Power law relationship between generalization error and dataset size was first thoroughly studied by this paper from Bio Research in 2017. By looking at practical models and datasets at the time, they identified these three different regimes. First, on the left is the small theta regime. And here there's not enough information and lead to random guessing predictors. In the middle is the power law region, and generalization error reduces as more data is added. And here the exponent captures how effective the model represents the data. And in the last regime is denoted as a reducible error regime, since there can be intrinsic error lower bound that can't be we can't go below. If we further look into their empirical findings, across many workloads, they observed consistent power law improvement of generalization performance with exponents ranging from 0.07 to 0.35. The workload spans machine translation, language modeling, image classification, and speech recognition tasks. And they've also varied choice of models, optimizers, and loss functions, and still observed this consistent power law behavior. So there was a question whether these power laws only have been observed in neural networks, and I think you could still Gaussian process or other kernel-rich regression also do show this power law behavior. I'm not sure about decision trees and boosting, and I guess I'll describe later in one of our models. We used kernel methods to explain some of this power law scaling behavior. And yes, the fact that we use the kernel method is due to relationship between very large width neural networks and kernel methods, but also the generic kernel methods can also show this power law behavior as well. Okay, and so more recently, Kaplan and McCallish et al. Observed also power law behavior in transformer-based neural language models as function of optimal compute, dataset size, and parameters. One thing to note is that how consistent this power law behavior is over many range of decades. This consistent scaling behavior powered and guided the development of GPT-3, and this is one of the most successful applications of scaling laws in deep learning up to date. Across many of these works, there has been consistent observation of power law-like scaling of performance with dataset and model sizes. The performance can be measured with the test loss, and this empirical findings suggests that the phenomenological relationship of the form can be described as the formula shown here. Arguably, one of the most interesting aspects of this formula is the scaling exponents. So it's natural to ask whether we can come up with some theoretical description for determining this exponents. However, looking at the literature, there seems to be a major discrepancy between predictions from theory of this exponents versus empirical observations. As far as we could tell, most of the previous work predicted a relatively simple integer or half integer exponent for the scaling exponents. However, as we've seen empirically with the models and data sets that used in practice, the observed exponent values are more diverse and interesting, and often observed to be much smaller in value. And one of our contribution in our paper is trying to provide a framework and theory describing this discrepancy. So now let's dive into the main content of our work. The main contribution of our paper is the identification or classification of 4 scaling regimes. I'll first give a brief high-level overview of these 4 regimes. The regimes can be split into whether we are scaling dataset size D or model size P, or whether we're in the underparameterized setting or in the overparameterized setting. So this 2x2 table characterizes the 4 scaling regimes of our interest. I want to note that in order to clearly distinguish different regimes, we're interested in the extreme underparameterization case where D is much larger than P, and extreme overparameterization case where P is much larger than D. These 4 scaling regimes can be further grouped into 2 separate categories. First of them is what we called the variance-limited scaling regime, and they correspond to this diagonal blocks here. Here in this regimes, we will observe relatively simple scaling exponent in accordance with classical theory result. The other category is denoted as the resolution-limited scaling regime, which corresponded to this off-diagonal blocks. Here we observe more interesting exponents, and this may be arguably where the practical deep learning models are being trained as. For example, in the case of large language models, we have much more data than number of parameters. We believe they operate in this underparameterized setting. We increase the size of model from a few millions all the way to hundreds billions in the case of GPT-3, trying to predict how performance improves in this underparameterized setting. On the other hand, for most image classification tasks, one could argue that we are operating in the overparameterized setting, as observed by the fact that the image models can even fit the random labels often. In this case, providing more data is crucial for improving performance. So let's first dive into explaining this variance-limited scaling first. One of our observations about this variance-limited scaling regime is that the scaling properties of underparameterized model with respect to D, dataset size D, and overparameterized model with scaling with respect to model size is simply described by existence of a well-defined infinite data or infinite model size limit. The scaling behavior comes from reducing fluctuations around this infinite limit, and as variance becomes smaller with more data and larger models. Though often not explicitly stated, this is the framework underlying most theoretical results in the literature, which leads to relatively simple exponents. To be a little more concrete, if you have a random variable A that concentrates around its mean A bar, with variance and higher moment scaling like some small number epsilon, then for any sufficiently smooth function of A, called fancy A, the mean concentrates around F of A bar with leading corrections controlled by the variance of A. One way such a concentrating variable can arise is from the empirical average over a large training set or over a large number of parameters. Can be even more concrete, focusing on the lower right corner and looking at the variance-limited scaling of overparameterized models. Recall from earlier talk given by Joshua, in the case of the wide network limit, neural networks becomes quite simple. And one concrete way that this simplification is realized is as under a gradient descent training, the training dynamics of wide networks approach that of the linearized model. And moreover, one can incorporate systematic expansions that capture the finite width effects, and this leads to the scaling behavior of the loss towards the infinite width limit loss. And it's if you analyze it, it's predicted to scale as 1 over width, which can be empirically verified. So here we see that due to the variance reduction as you increase the width, the test loss will approach the infinite width loss with scaling exponent 1 when you look at as a function of width. Very similar story for variances around infinite data limit can be made for the underparameterized case as well. Here, the cartoon illustration is describing the local solutions in the infinite data case for the solid line versus finite but large data case in the dashed lines. Corrections to the central limit behavior leads to the loss deviation at the order of 1 over d. And this will lead to the variance-limited scaling. Here, we empirically tested the variance-limited scaling for a variety of architecture and dataset. You can observe the universal and simple dataset independent variance-limited scaling exponent of 1 on these plots. The predicted scaling of 1 with scaling respect to dataset size D or with W can be observed for varying choices of dataset, model, and loss type. Also, since actual number of parameters scales as quadratic respect to the width, this would lead to exponents of 1/2 with respect to the number of parameters. Although we can empirically observe this universal scaling, in practice, what would be interested in is away from this variance-limited scaling regimes. So now let's see how scaling law or scaling behavior occurs in this in the resolution-limited regimes. Here, the relevant blocks are the scaling of the dataset in the overparameterized or scaling of the model size in the underparameterized case. Again, this is the interesting regime, since we are providing more of what the limiting resource is and observe how the performance improves. So how can we understand this resolution-limited regime? There is a simple geometric picture, which, if true, allows us to derive an interesting scaling behavior. Here, we're imagining the data is drawn IID from small d-dimensional manifold, and the target is a smooth function f. Imagine what a neural network is doing is the following. With large enough model, we can fit the training data targets perfectly, which is here depicted as the blue dots. Given a new test point denoted with the purple dot here, the test prediction from the model can be given by the target value of the closest training point. Here, the closest training point is to the test point is denoted by the purple circle around the blue dot. And this is how the model is making predictions. Here, small f denotes the learned function, and the fancy f denotes the smooth target function. And in this model, the prediction is coming from the closest training point target value, where the model has already learned perfectly from. If that's the case, we can analyze how the test loss behaves. Expanding the test loss near the closest training point by Taylor expansion, we get the leading quadratic behavior since the loss vanishes at the training point. If we want to find how the loss scales as you increase more data, we can use a simple relationship converting volumes to distance for typical nearest neighbor distance when sampled IID points. So if you sample the points, and this relationship comes from estimating the nearest neighbor distance of d number of points in dimensions small d. So this relation comes from, as you add more data, the typical distance becomes smaller, but in higher dimensions, the distance will decrease slower. And this functional form captures that effect. The exact constant 2 will depend on the assumptions on smoothness of the target function and the assumptions of the learned functions. Here, I'd like to emphasize that in this simple toy model, one can actually obtain some non-trivial scaling exponent value that's given by this 2 over d. And this is dimension d dependent and could lead to non-integer and often become quite small value. A very similar setup can be studied for the underparameterized model and how it scales with the model size. In this setup, instead thinking that data is drawn from a smooth d-dimensional manifold, we can consider data itself is the d-dimensional manifold, since we're effectively taking the number of data points to be infinite. This can be a good model. Then adding more capacity to the model will allow to better approximate this data manifold. You can imagine for relevant networks, if you increase more number of parameters, it's adding more of the piecewise linear region where you can represent this data manifold more effectively. And if you think how this number of linear regions scale with number of parameters, then this will tell you how the test loss will scale with number of parameters. And here, the relationship is similar to the overparameterized case, where you get the exponent that dependent on the dimension of this data manifold. And here also, the constant depends on how well you're approximating the function, how this function approximates the data manifold. And here, generically, we'll have a non-integer or non-half integer and non-trivial exponent in scaling of the model parameters. And if we go and measure these exponents ourselves, we find the data-dependent non-trivial exponents are actually observed in this 2 resolution limited regime. So all this scaling regime can be also explicitly analyzed in a more relatively simple model than actually analyzing more complicated neural networks. Well, we'll be using a linearized model with some nonlinear random feature, which leads to simple kernel methods. Using the kernel methods or linearized model is motivated by the fact that in the large width limit of neural networks, they become this linearized or kernel methods. So the toy model that we're gonna use to analyze is this linear random feature model, and we're also going to use the teacher-student setup, where both data generating teacher and learning student is a linear model with these features f, fm's and fmu's here. And we'll take the student features, the randomly selected subset of the teacher feature for simplicity. In this setup, everything is determined through these kernels between two data points, which is defined as the covariance function of using the features. And expected test loss is given by this formula is of data set, training data set size D comes from mismatch between the full data distribution and the finite draw of training set size D. And the full test loss is given by with this expression with kernels. And the question is how to extract the asymptotic large D dependence with these expressions. In order to make further progress in this approach, we need to take some ansatz on the properties of these kernels. One hint comes from actually looking at the eigenvalue spectrum of these kernels on a real data set. And if here we plot the kernel spectrum on the pooled MNIST data set, and we observe that the kernel eigenvalue spectrum follows power law behavior. And we can model the decay of the kernel eigenvalue as this the power law formula. If we make this ansatz for the kernel spectrum, then we can actually use this fact to compute the large D dependence of this test loss, either by using the replica trick coming from the statistical physics, or sometimes even more simply by making even further assumptions that this kernel spectrum exponents are large, then the test loss scaling only comes from the tail eigenvalues beyond the dataset size D. So the test loss will come from the contribution of the tail eigenvalues from D+1 to infinity. And using this power law scaling behavior of this power law relationship between of the kernel eigenvalues, we can obtain that the test loss will scale with dataset size with scaling exponents given by the kernel the kernel exponent. In pictures, if we assume power law ansatz for kernel eigenvalues, this will lead to power law scaling with respect to D. And very similar argument can be also made for the model size. And this also will lead to the model size scaling P with the same exponent alpha K. And here, this is one realization of the duality between the dataset size D and model size P. So here we observe the same scaling exponent appear for scaling, dataset scaling and the model scaling. So there is a question: what affects the scaling exponent for neural networks beside architectures? Do optimizers make a difference? Is there any reason to believe that second-order optimizers will give rise to different training dynamics? So I think this is still an open question, and our framework doesn't quite address this this question. So there's a potential that different optimizer could lead to different scaling exponents, but there has not been a conclusive result yet. That's as far as my understanding. So to close off on the assumption about the kernel spectrum, we found that there are classic results bounding the kernel spectrum by the dimension-dependent exponent, and it gives a power law with relatively mild smooth assumptions. And this type of work goes back to Weil from 1912. And these bounds are often saturated for generic and smooth kernels, which then predicts generic power law decay spectrum of appearing in kernels for generic cases. So again, to summarize with this illustration, if you assume some smooth generic kernel, which will lead to power law scaling of the kernel eigenvalues, and which in turn will lead to power law scaling with dataset size and model size with interesting exponent coming from the kernel eigenvalue exponent. And the fact that this exponent comes from the kernel spectrum exponent leads to the duality between dataset size scaling and the model size scaling. And we tested this observation for all of our 4 scaling regimes. Here, so in this plot, we're basically looking at the scaling behavior of this teacher-student linearized model or kernel setting. And here, the varying colors being varying dataset by different pooling size of MNIST dataset. And in the variance scaling region, in the variance-limited region, on the diagonal, we observe the universal exponent of 1, or at least very close to 1. And for the off-diagonal resolution-limited scaling region, we observe the non-trivial exponents. And we can also identify rough duality in the dataset size exponent and parameter exponent if you match the colors on the off-diagonal plots. So after identifying these 4 scaling regions, we also investigated scaling exponents in the realistic neural networks and trying to understand what could lead to change of the scaling exponent. So this goes back, it's loosely connected to the questions that's asked earlier. First, here we show that this kernel or linearized model setting prediction can be observed. The prediction can be observed empirically beyond the teacher-student setting. So here, what we're doing is we're using the pre-trained feature coming from EfficientNet V5 trained on ImageNet classification, and we take the features coming from the penultimate layer and doing the transfer learning to the CFAR10 classification task. And using this penultimate layer feature as our random features, we can also observe all these 4 scaling regions. And the plot may be not as nice as the teacher-student setting. We can observe the relatively simple exponent on the diagonal and the non-trivial exponent and the duality on the off-diagonal plots. Here, we're studying some variation on the properties of dataset. So on the left, we varied superclassing scheme for CFAR100 labels, resulting from 5 classes to 100 classes And we observed that the scaling exponent doesn't noticeably change as you vary a superclassing scheme. On the right, we added Gaussian noise to the inputs with varying noise scales. And this has strong effects. We observed there's a strong effect to the exponents. And this result suggests that what model is mostly learning is information on the input manifold rather than the target manifold. And, and in this set of experiments, we varied the architecture and changed the widening factor and depth for white resonance when we were doing the classification task on CFAR10. And we observed that a widening factor affects the scaling exponents, whereas the variation on the depth doesn't matter as much. So there's a question. Is the scaling exponent of given neural network architecture related to the exponents of its corresponding NTK? So would it be possible to compare the exponents of different architectures just by analyzing the NTK spectra instead of needing to empirically train them for many different values of data? Right. So yes, I think in the very large width limit, where we can think of the neural networks as similar to linearized models, and the kernel associated with the linearized model is NTK. And in that setting, the kernel eigenvalues of the NTK, the eigenvalues of the NTK, if you just look at their decay and their exponent, is the kernel exponents that I talked about earlier, and that will correspond to, they'll give the scaling behavior of both the dataset size and model size scaling in the case of the teacher-student setting. So, and actually the closing the gap from the teacher-student setting to more realistic data setting is one of the yes, remaining future work. And yes, if you naively try to use that prediction, it doesn't work as nicely. Sometimes it does work, but it doesn't work as effectively as we've seen in the case of teacher-student case. But yes, it's a good question. And most of the results I shared today were done in collaboration with these amazing people, Yasman, Ethan, Jared, and Karsh. And to sum up, we identified 4 scaling regimes where scaling, when scaling dataset size and model size. This is divided into whether we're in the underparameterized or overparameterized setting. And among these, dataset scaling in the underparameterized case and model size scaling in overparameterized leads to the variance-limited scaling, where exponents are coming from reducing the variance and leads to simple exponents. For dataset scaling in the overparameterized case and model scaling in the underparameterized case, we identify them as a resolution-limited scaling regime and find more interesting exponents with some geometric origin. We also use the linearized model, which has a kernel method, which is related to kernel method to realize this interesting regimes and identify the duality of the resolution-limited regimes. Uh, One of the main motivation of this endeavor was that better understanding of scaling laws would guide how to make progress when we're given more compute to process more data and larger models. Hopefully, our theory and empirical observations would be useful starting guide for those endeavors. Certainly, our work has a few limitations, and we hope to find even more comprehensive framework and better models for understanding neural network scaling behavior. And thank you for joining today. I've certainly had fun preparing and presenting this talk. And thank you.
Okay. I don't think you have any other questions. So thank you very much for the presentation.
Yeah,
And
thank you
for
for the
everyone
invitations.
watching, please join us again next week. Okay, bye.